Okay, the the homework of this week was about groups with small order, right? Groups of small order. Let's first focus on abelian groups. So we have commutative or abelian groups, and we have non-commutative or non-abelian groups. Today, let's focus on these groups, the groups which are commutative. So for any two elements A and B, AB is equal to BA. Okay, so the order of a group, which we showed with this notation, this means the order of group is the number of elements of the group G. In the case where G is finite, it's a finite number. If it's not finite, it would be infinite. So, well, that was trivial, right? So let's consider the simplest case. A group with one element. Is there any group with only one element? You can unmute yourself. We can discuss it now. You can just report.
With like only the identity element?
Yeah, that's the only thing, right? So if a group has one element, there should be just one thing here. But we know any group is supposed to have identity elements. So it would be just identity element. And then E times E, we should define the operation is of course E. And E inverse is E. So it is closed under this multiplication. It has inverse, and of course it has identity. So there is one group with order 1, and that's trivial. Okay.
I have a question.
Yep.
Can you only, like, could that group be abelian or no, since there's only one element, and I feel like you would need two?
Yeah, so of course, if you have just one element, it would be abelian because E times E is the same as E times E. But if you want to make it slightly different, you need two elements.
Okay.
Yeah, but the point is that when you say abelian, you say AB times BA, right? Here, you don't say A and B are different things.
Yeah,
I mean, in this case, A is equal to B equals to A, equal to E. Mm-hmm. In this case. So if I got your question correctly, that would be the answer. So yeah. Okay. So if the group has two elements, one of them has to be identity. There should be something else. Let's call that A. It's just a letter to show the other element. I want to see if there's any group with two elements, or well, in other words, I want to find all groups with two elements. Okay, so in order to completely understand a group, one way is to look at, or completely describe a group, one way is to look at the table for a group. So we have E, we have A, we have E, we have A. And this is the multiplication of the group, or the operation, or the operator of the group. So E times E is E. Here it means E times E is E. E times A, this is E times A. Because E is identity, should be A. Here is A times E. Again, because E is identity, this one should be A. And this one should be A times A. Okay, it's either E or A. But can I choose any one I want, or it can be only one of them? Or it can be A. Is it possible for this thing to be E, or is it possible for it to be A? Which one would work? It's quite simple. You can give me your answer. Yes. At least E is an answer. What about A? Why I can't have A there?
I think because it would be a squared, and then since the order is 2, any like the order is like the least factor, whatever that makes it equal to the identity. So it would
Yeah.
be.
Yeah. Okay. So what you're saying is that okay, let me erase some of these. So what you're saying is that A squared would be A, right? That's what you're saying. So what does it mean? Well, what would be A inverse? It doesn't matter what is A inverse, but multiply both of them by A inverse. Whatever A inverse is. On the left-hand side, we get A, because A inverse times A squared is A. On the right-hand side, we get E, and A equals E. It's a contradiction, because then this group wouldn't have two elements. If A and E are the same, G would have only one element. And that's not correct. Okay, so A, because A is not equal to E, therefore A squared can't be equal to A. So A squared has to be E. So there's just one group with two elements, because everything is fixed now. There are no choices, you know, everything is kind of forced to us. So there's just one group with two elements, but you already know that. What is this group with two elements? What is G? You already know this group, I guess. Does anyone know the name of this group? Okay, I would write it. It's just Z2. And you can see that. Look at this table here we have. Actually, instead of, well, Z2, we know Z2 contains 0 and 1, right? 0 is the identity and 1 is the other element which we are showing with A, right? So this is 0, this is 1. This is 0, this is 1. And 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 2, which mod 2 it's going to be same as 0. So there is just one group with two elements. Any question? Okay. What about groups with two elements? Find three elements. Find all groups with three elements. Do the same thing yourself. Try to find the table. Think about that for a few minutes. Okay, so find all groups with three elements. Okay, I want to find all groups with three elements. Now, what should I do? So let's first say we are looking at the abelian groups. Or maybe not. Maybe we can just, I can tell you the theorem directly. So I have there's a theorem which completely answers this question in a lot more general sense. The important thing here is that 3 is a prime number, but without thinking about that stronger theorem, let's first just try to solve it by hand. So if G is a group with three elements, one element would be identity, right? There would be two more elements. Let's call one of them A, the other one B. I have three elements here, right? I can look at this table for these three elements, E, A, B, E, A, B. Okay, let me tell you a secret. Whenever, it's not a secret actually, but whenever your group has finitely many elements, like here, there's just 3 elements, right? In each row and in each column, we should see all the elements. So here, for example, here I should write what is E times E. E is identity. Identity times identity is identity. What is identity times A? It's A. What is the identity times B? It's B. See, in this column, we have EAB. We have all 3 elements. That should be true for each row and each column. So look at this column, for example. Here we have E times E. It's E. The next one, here it's A times E. A times identity is A. And the next one is B times identity, which is B. Now, for example, if I want to fill in this row, I should have all the elements E, A, and B. I already have A. So at the remaining 2 places, here and here, E should be in one of them and B should be in the other one. Okay, does it make sense? So I should decide. I should decide what is the first one. Maybe I can change the color. So I should find what is A times A, and I should find what is A times B. Okay, A times A and A times B. Okay, so as I said, A times A, because we want all 3 elements E, A, and B in this row, it should be either, and we already have A there, it should be either E or B. So it's E or A times B, oh, sorry. A times A is the other one, which is B. Okay. Which one is correct? Is there, do you think there's a difference, or I can choose any of them I want? What do you think? For example, is it possible for A times A to be E? Is this possible? Why? Okay, someone said no. And I'm asking why it can't be E. Oh yeah, that's very good. It has order 3. So the group G has 3 elements, right? It's an important theorem that the order of each element should divide 3. Now here, if A times A is E, it means A squared is E, right? So if A squared is E, it means the order of A is 2. But 2 does not divide 3. And we can't have that. So this is not possible. Is it clear for everyone? So if A squared is not E, because we already have A, it has to be B. Also, as I mentioned, in each row, we should have all the elements. We have A and B, so this one has to be E. So A times B is E. Okay, let's look at the other one. Look at this column. We already have A and B. So the next thing which appears there should be E. There is no other choice. And in this column, we already have B and E, so the next thing has to be A. Now, there is something which is interesting, and that's the fact that everything is kind of forced to us. We didn't have any option, right? Everything is kind of fixed. There are no choices. It means there is exactly one group with 3 elements. There is just one group with 3 elements. And you already know one group with 3 elements. What is that? That's Z3, right? 0, 1, 2. So here, 0 is the identity. So 0 is here. But which one is 1? Which one is 2? Is A 1 or is B 1? Which one is 1 between A and B? And which one is 2? It's a very interesting question. I want to say E here is, because there's just one group with 3 elements, and Z3 is a group with 3 elements, so this G has to be Z3. So the elements should be the same as elements of Z3. Here the identity is 0, here the identity is E. So E is 0. Here we have A and B. In Z3 we have 1 and 2. So A is either 1 or 2, B is either 1 or 2. Okay, Victoria says A is 1, B is 2, and she's right. Any other answer? Can I choose A to be 2 and B to be 1? Is that wrong? Okay, let's try what she says. She says A is 1. Okay. If A is 1, 1 plus 0 is 1. And if A is 1, B is 2. So, and 0 plus 2 is 2. Yep, it works perfectly fine. So then 1 plus 0 is 1. That's correct. 2 plus 0 is 2. That's also correct. Here, let me erase it. Here we have B. Now it should be 1 plus 1, which is 2, and B is 2. So it's also okay. There's nothing wrong here. Here we had A, sorry. Here we had A, now we have 2 plus 2. 2 plus 2 is 4. 4 mod 3 is 1. And 1 is equal to A. So it is also correct. So what you said that we can take A to be 1 and B to be 2 is correct. So let me write it here. So in order to show G is equal to Z3, we can say E corresponds to 0. We can show A corresponds to 1 and B corresponds to 2. What if I tried the other way around? What if I say, well, E is 0, of course. But what if I say B corresponds to 1 and A corresponds to 2? Is there going to be any problem? Let's see that. Let's first understand what do I mean by problem, and then let's see if that also works or not. And then we would get to a conclusion. So here we have 0, 1, 2, 0, 1, 2. 0 and plus. 0 plus 0 is 0, 1, 2. 1, 2, 1 plus 1 is 2, 1 plus 2 is 3, which is 0, 2 plus 1 is 3, which is 0, 2 plus 2 is 4, which is 1. Right? And here we had, sorry, here we had E, A, B, E, A, B. It's E, A, B, it's E, A, B. I said A squared is B, is E, AB is E, AB is E, and B squared is A. Now, would it be fine if I say, well, E is 0, we know that. Would it be fine if I say A is 2 and B is 1? wouldn't everything work the same? Look, 0 plus 2, or 0 plus a is 2, or a. 0 plus b, or 0 plus 1 is b, so it's 1. Here, 0 plus 2 is 2, 0 plus 1 is 1. Here I have 2 plus 2. 2 plus 2 is 4, mod 3 is 1. And a plus a is b, so that would be 1. And 1 plus 1 is 2. If you look at this table, you would see if I, rather than choosing the first thing, sending a to 1 and b to 2, if I say b is 1, b is just another name for 1, and a is just another name for 2, there would be no contradiction. By that I mean, for example, if b is 1, if I say b is 1, b plus b should be equal to, or b star b should be equal to 1 plus 1. 1 plus 1 is 2. If you look at this table, b star b is a. And here we say a is 2. So there is no contradiction. So it seems it doesn't matter if we say a is 1 or b is 1, or a is 2 or b is 2. Is it clear to everyone that in this table, so if you look at, so if I erase these extra things, if you look at the table on the right-hand side, if you look a little bit carefully, there's a symmetry between A and B. There is really no difference between A and B. If I just move this column here and just move this row there and move this column here, which B comes before A, you would feel that I have changed the roles of A and B, because A and B are really symmetric. There is really no difference between A and B. So no real difference between A and B. Does it make sense? Okay, just tell me if you understand what I mean by that or not. Because it's an important issue here. Okay, yeah. So there is really no difference between A and B. But doesn't that imply that there is no difference between 1 and 2? So, I mean, we usually tend to think 1 is less than 2, right? 2 is 1 plus 1. So we usually think 2 is 1 plus 1. So 1 should be different with 2. How can I say the roles of 2 and 1 are exactly? So if A and B, they have very symmetric roles there, 1 and 2 should have very symmetric roles here. But it is true. Even here, the reason we think 1 and 2 are kind of have different roles, because we think about Z, not Z mod 3. Here, it's correct that 2 is 1 plus 1. But also, what is 2 plus 2? It's 4, which mod 3 is 1. As you can see, 1 and 2 are, they completely have symmetric roles here. There is no really natural like difference between 1 and 2. So I can, so if I see, you see, so if I, instead of everywhere, instead of 2, if I write 1 and instead of 1, I write 2, nothing would change. No, it doesn't make any difference. 1 and 2 have completely symmetric roles here. So it's good to think about them just as kind of A and B, because it makes more sense. It gives a better feeling that they have completely symmetric roles. We have some understanding about 1 and 2, which comes about from natural numbers, but these are elements of Z3 and not natural numbers. Okay, so Z3 is the only group with 3 elements. Now let's continue with group with 4 elements. Find all groups with 4 elements. Okay, think about it for a few minutes. we want to solve this completely similar to the previous one. I really want you at home to, even if you're like, if you're in the meeting right now, I want you to have a paper and a pen or pencil next to you, and I really want you to solve this, just like we used to do in the class. I really want you to try to write them for yourself. Don't just look at your tablet or your laptop, okay? Try to solve it. And even if you're watching the video later, because some people might have gone back to their own country, and because of time zone, they might watch the recorded video, you can do the same, because I give you some time to think about it. So please try to solve the question for yourself, especially if you're watching the recorded video. You can pause and you can spend as much as time you want and try to solve it and then play again. Okay, someone wants to say something. Victoria, you want to say something? Yeah.
When we were classifying these in class, she also used a group of order 3 as the cyclic group of G, like little g.
That is correct.
Not the same.
Yeah, but we already, you know, because when we looked at the table, we noticed we don't have any, there are no choices, right? Everything is forced to us.
Yeah.
It kind of implies there's just one group. So it doesn't matter what you say or how you find it. They all have to be the same because there's just one group, right?
Yeah. Okay.
So they're all equal. But you're perfectly right. I would mention that.
Okay. Thank you.
Yeah, good point. Thank you. Okay, so if you have a group G with 4 elements, one of them should be the identity. The other ones are A, B, and C. And we should look at this table. I think they call it Pseudo rule. But the way we're looking at this table, and we're trying to have all different elements in each column and each row. So the multiplication is a star. We have A, E, A, B, C. Here we also have E, A, B, C. So E times E is E, A, B, C, A, B, C. Okay. So we start with A squared. We should decide about A squared. A squared can't be A because we already have A in that row. So it should be something between E, B, and C. We should choose one of these. Okay. One thing to note is that the order here doesn't really matter. There is no really difference between between A, B, and C. I mean, it's not like, you know, in a group, we don't have naturally an order. there is no, it's not like there is a order between them. So A, B, and C are just notations. So at this point, there is no difference between B and C. So we can just say A squared can be B, because being B or being C, they're not different, really. There's still a symmetry between them. So it's either E or it's something else, right? I would call that something else. I would call it B. So the only point is that if A squared is E or not. Is it possible for A squared to be E or not? Yes, it is. Well, yeah, it is possible. So the point is that G here has 4 elements. So the order of every element should divide 4. So the order of every element should divide 4. So the orders of elements here in this group can be 1, 2, and 4. The only thing with order 1 is identity, right? If there is anything with order 4, if there is something with order 4, so let's say A. If A has order 4, it means A squared, A cubed, and A to the 4th, which is the same as identity. They are all different elements. These 4 things, they are different. They are not equal. So let me erase here. Maybe even this one. So if order of A is 4, I claim A squared, A cubed, and A to the 4th, which is E. These are 4 different elements. Why? So let's say 2 of them are equal. What will happen if A is equal to, say, A squared? I can multiply both of them by A inverse. I would get, sorry, not 1. E equals A, but E is not A. A is another difference, so it doesn't make sense. Or if, say, A squared equals A cubed, I can multiply them by A inverse 2 times. Again, I would get E equals A, which is not correct. So these 4 things are 4 different things. So in another word, and the group has 4 elements. So G, which is E, A, B, C, is equal to A squared, A cubed, and A to the 4th. So in other words, A generates the group. When the powers of A gives us all the elements, we say A generates the group. What's the name for such a group? What do we call this group? You know the name, right? I want someone to tell me, what do we call such groups, which there is one element which generates all the group? Yeah, that is correct. And we already know what is that group with 4 elements. It's Z4, which is 0, 1, 2, 3. Which one is the generator here? Which element is Z4 is the generator? Is it 1? Well, it seems 1 is correct because we can have 1. We have 1 plus 1, which is 2. 1 plus 1 plus 1, which is 3. 1 plus 1 plus 1 plus 1, which is 4, which is 0 here. So 1 generates Z4. But what about the other elements? What about 2? Does this one also generate Z4? Let's see. We have 2 plus 2, which is 4. 4 mod 4 is 0. And 2 plus 0 is 2, and 0 again, etc. So 2 does not generate Z4. What about 3? We have 3. We have 3 plus 3, which mod 4, it's 6. Mod 4 is 2. Then we have 3 plus 3 plus 3, which is 9. Mod 4, it's 1. And 4 times 3 is 12. Mod 4 is 0. So 3 also generates Z4. So it's kind of interesting. In the previous example, I told you in Z3, I told you 1 and 2, they have similar roles. That's the case here. 1 and 3, they are completely similar here. And 2, but 2 is different. As you can see, 2 has a different role. So there's a symmetry between 1 and 3, but not between 2 and the others. Okay. Is it the only group with 4 elements, or is there anything else? That's the question. So if you're looking for another group with 4 elements, this other group, so let's say we're looking for another group with 4 elements. In the previous case, we assumed there exists one element with order 4. So now if you want to find another group, we should assume there is no element of order 4. So the order of, so if I write G as E, A, B, C, because the order oh, thank you. From where? So I was saying, so I'm looking for another group with 4 elements. And in the previous case, we assumed there exists an element of order 4. So if I want to find another element with another group with 4 elements, I should assume there is no element of order 4. On the other hand, because order of each element divides 4, so the only potential things are 1, 2, and 4. Because 4 is not one of them, the orders can only be 1 or 2. But the only element with order 1 is identity. So the other things here, A, B, and C, they all have order 2. They're all of order 2. So A squared is identity, B squared is identity, C squared is identity. Okay, let's use this as a fact to see what we can do. We have our table, E, A, B, C, E, A, B, C. A squared is identity. B times B is B squared is identity. C times C is identity. What about the other things, like these two? The point now, the important thing is that there is no difference between B and C yet. I mean, B and C are just two notations. There is no difference between B and C. We can just change, there's a symmetry between them. I can just, instead of B, I can write C, and instead of C, I can write B. So I want to see what is A times B. It's where we start to kind of break this symmetry. So A times B, because we should have all the elements in this row, it should be either B or C, because we already have A and E there, right? But is it possible for A times B to be equal to B? If that was the case, we could multiply both of them from right-hand side by B inverse, and we would have get A equals E. If I multiply everything by B inverse from right, on the left side, I would get A, B, B inverse, which is A, and on the right side, I would get B, B inverse, which is B. Therefore, A would be identity, but that's not correct. We're assuming A is another element. So AB is not B. The only thing which remains is C. So now look at this row. We have A, we have C, we have E. The blue one has to be B. Now we are almost done, because if you look at the yellow thing there, in this column, we have C, we have B, we have E. The only thing we don't have is A. Now look at the green one, green box. We have A, we have B, we have E in that row. What we don't have is C. Now look at this new blue one. We have A, we have C, we have E, we don't have B. And finally here, the only thing we don't have in this column is A. So we got another group. So this is a new group. So G, group with 4 elements. It either has an element of order 4 or it doesn't have an element of order 4. The thing is that as soon as we decide about that, the group is fixed. As soon as we decide if G has an element of order 4 or not, everything is forced to us. So when I assume G has an element of order 4, there are no options anymore. So there's just one group with 4 elements, which has an element of order 4, and that's Z4. And there is, as soon as we assume G doesn't have any element of order 4, again, everything is fixed. So there is just one group with 4 elements such that it doesn't have any element of order 4. And we already know one group with 4 elements, which it doesn't have any element of order 4. Does anyone know what is that group? You can unmute yourself and you can just say it if you know what's that group. So we have just one group, G, which G has 4 elements, but no element of order 4, or in this kind of equivalently, but not cyclic. There's just one such a group.
Is it like Z2 cross Z2 or no?
That is correct. So Z2 has 2 elements. Z2 has, again, 2 elements. Therefore, Z2 cross Z2 has 2 times 2, which means 4 elements. And this one is not, doesn't have any, it's easy to see, it doesn't have any element of order 4. So you are right. So let's just check this fact and make sure we're not making a mistake. So Z2 is 0, 1, 0, 1. So the good thing about groups is that we can look at the product of groups. So it is going to be pairs of elements of the group. 0, 0, 0, 1, 1, 0, 1, 1. Okay, so the order of 0, 0 is 1 because 0, 0 is the identity here. Order of identity is always 1. What is the order of 0, 1? Let's see. 0, 1 plus 0, 1. The operation here is component-wise. So we have 0 plus 0 and 1 plus 1. 0 plus 0 is 0. 1 plus 1 is 2, but it's in Z2. And 2 in Z2 is 0. So the order of this element is 2. What about 1, 0? 1, 0 plus 1, 0 would be 1 plus 1, 0 plus 0. 1 plus 1 is 2. But again, 2 in Z2 is 0, so it's 0, 0. So the order of this element is also 2. Similarly, the order of the last element is also 2. So there is no element with order 4. So what we have here, our table is actually Z2 times Z2. And yeah, yep. So if G has 4 elements, so if G has 4 elements, it's either Z4 or Z2 times Z2. And that's it. Now, just in the last minute, let's look at the groups with 5 elements. Actually, more general than that. Actually, if you have a group G with P elements, where P is a prime number, we know order of each element should divide P, right? Order of any element should divide P. But when P is prime, the only natural numbers which divide P are 1 and P itself. The only element with order 1 is the identity. So every other element in the group G, their order should be P. So order of every element in G, element which is not identity, is P. So let's say A is an element such that order of A is P. So if we look at A squared, A cubed, up to AP, just like the case of the previous case, which we were looking at Z4, which there was an element of order 4, these are P different elements. So there are P of them. And G has P elements, so it has to be G. So G would be, we can generate G with just one element. So it means G is cyclic. And this is actually ZP. So if the order is prime, there's just one group, it's ZP. So for example, when the order of G is 5, there is only Z5. If it was 7, yeah, one of them is E and the rest of them have order P. Yes. And the last one is identity element, because I'm assuming the order of A is P. So A to the P is, yeah, you're welcome. A to the P is identity. So if the order of G was 7, it would have been Z7. If the order of G was 11, it would have been Z11. If it was 13, it would have been Z13. That's the case for every group with prime order. They are cyclic, they are Z to that prime order. Okay, that's it. Is there any question? If not, stay healthy, stay safe, stay in home, study, and have fun. Take care of yourself, guys. Okay, bye.